Hi, welcome to Llama Open Intelligence for Everyone. I'm Joe Spisak, Product Director at Meta, focused on our open source and ecosystem. So it's really exciting that LLMs, especially Llama, are really becoming foundational to this next wave of AI. And it's not only the LLM, but also things like text to image generation, or even AI enabled creator tools that basically take the power of all of this AI and put it into the hands of those who can build new things and new applications. So there's three things I really want to talk to you today about. One is really our open approach with Llama, the systems that are actually forming around Llama. So it's not just a model anymore, but really a system and really ultimately an agentic application. And then three, how we think about trust and safety, and especially the tools and the ecosystem around us in open trust and safety. So just kind of taking a step back and looking at where we were and where we've come from, it's actually a pretty incredible journey from Llama 1 back in February to Llama 2 in July last year to the Code Llama and code generation models we released last year, as well as Purple Llama for open trust and safety to, most recently April with Llama 3 and last week, of course, the big bang we had with Llama 3.1 and the 405B launching. And all along the way, we've been releasing system level components that help you to build Llama much more responsibly and much more safely. So just zeroing in on the 405B for a second, we are really excited about this model, and we're really excited that we were able to open source it. We really feel like this is going to supercharge innovation, open up completely new application areas like synthetic data generation to improve smaller models. And this is a model that is open weights, open source. You can fine tune it, you can distill from it and create smaller models. You can deploy it yourself on your prem. You can even distill it onto a mobile device. So really, it gives you the full freedom to take this frontier class model and really make it your own. And when we thought about the 405B and this new class of models we built, we started with simplicity. And the architecture is, an autoregressive transformer architecture. It uses, special attention to make it faster at inference time. But ultimately, we pushed on scale. We pushed on the scale of data and we pushed on the scale of infrastructure when we were training it. So when we thought about data, it was, how much further can we push data? And we ended up around 15 trillion tokens, which is some of the largest data ever trained in LLM. And then 16K H100 GPUs. This is by far the largest infra we've used to train a Llama model to date. And the results are spectacular. If you compare Llama 405B, and we've done this across over 150 benchmarks against some of the top models in the world, Llama 3.14 by B definitely stands and compares really well to GPT-4o and Claude Sonnet 3.5, which are considered some of the best models in the world today. And it's not enough to do, kind of standard evals and static benchmarks. We also look at how humans and how people actually interact with our models and how well they perform. And you can see here, Llama 405B compared to, say, the GPT-4o or Claude Sonnet stands as well really well. I mean, does a really good job. The people loved interacting with them. This was over almost 2K prompts and over use cases like, say, being a coding assistant or a multilingual chatbot. And so we take a step back and think about, why open source is good. It's really good for developers. As I mentioned, these weights are weights that you can download, you can modify them, you can create custom applications on them. You have the full freedom to do what you need to do for what you need. For Meta, it gives us a chance to accelerate our development. There's new things happening in the community every day, and being open and building that bridge helps us to move faster and learn faster. And then really the world and how we democratize this technology and provide it for everyone, it kind of levels the playing field for the entire world. And our ecosystem is also flourishing. The ecosystem around us is not only enterprise, but it's also platform developers, startups, those building differentiated offerings like, say, Grok for really low latency inference, all the way through to our hardware vendors who are accelerating Llama models on various platforms. This gives the whole community kind of this platform to build on and really accelerates kind of all aspects. And you can see some of the launch partners we had with the 405B. Every checkbox here was a labor of love and night or a weekend or a lot of effort from a lot of engineers to make this happen. And you can see all the various use case and workflows that are enabled on day one with the 405B. From, say, Databricks to Dell to Grok, you can see all the way from inference to model distillation to synthetic data generation services. We really have a full gamut of services available for developers on day one. So let's switch gears and talk about the Llama system, because the model is only part of the story. And we think about how models actually fit within these agentic applications, we're evolving very quickly to having system safeguards and customizable system safeguards that you can then fine tune and customize for yourself. And today we call those Llama Guard or Prompt Guard. We'll talk about more in a second. But there's also tool use and how you actually plug in these models with, say, outside tools or plugins, or think about it in terms of like a search application, or say calling a calculator, because sometimes LLMs don't do math very well. So really building this whole capability, but with the model itself at the center of it. And we actually open sourced all of this. So we have a full repo. It's called Agentic Systems in the Llama repo on GitHub. And you can actually play with all the code yourself. And so we've also taken it all the way to demo apps. So you can actually build on our own demo apps that we have that use all of these components. In this case, what I'm showing is code generation and say like a coding assistant, where the LLM will generate code. It'll actually execute the code through a code interpreter. You can see it's generating some nice graphs using something like matplotlib. And ultimately, you can use this as a way to kind of build on top of it and kind of customize for your own. So it's not just the kind of the raw code. We actually provide end applications. And the last thing around systems is we're also working with the ecosystem to build and support kind of standardized ways to integrate with Llama models. And we think this is really going to accelerate kind of the world around Llama and the ecosystem. And we have an open RFC. It's linked here. It's on GitHub. We had dozens of comments so far. And ultimately, we want this to be kind of the glue that brings this community together and helps accelerate the overall ecosystem. So let's switch over to trust and safety, something near and dear to my heart. So when we think about trust and safety, and we think about the development process we've taken to develop these models, it really starts with the data and how we think about things like representativeness of the data set itself, how we think about evaluating that data for things like harmful content, filtering, benchmarks and evaluations. We obviously do some model level work as well. So we do things like safety fine tuning, but ultimately we bring humans in the mix at the end, or actually iteratively, things like red teaming. And when we try to jailbreak our models or understand what situations these models are going to be in, and actually have real humans interacting them, so we can actually iterate quickly and understand how to improve them, version over version. And so when we think about open trust and safety, one of the things that we thought about early on was we really don't want to compete on safety. It's not something that makes sense to compete on. We really want to do this as a collaborative effort, and hence a lot of our work in, say, AI Alliance and what's called really Purple Llama, which you can see some of the components here. And much like the system level components I talked about earlier, some of the things we've released are Llama Guard, which is a open model for prompt filtering, input and output, Prompt Guard for prompt injection attacks, Code Shield for things like insecure code generation. And ultimately, we have, I would say, the state of the art in cybersecurity evaluation, and we just released version 3 of that. And so kind of putting some numbers behind all of this, we've been at this in terms of research for over 10 years. The fundamental AI research team is world-class in this research. We publish system cards for our products, over 20 of them to date. We have over 100 members in AI Alliance, where we founded that effort with IBM last year. And we've open sourced over 1,000 projects, including PyTorch, obviously heavily invested in Llama, React, and a whole bunch of other projects. So this was incredible. Obviously, the models are fantastic, and we're really excited about what the community is doing with them. But the challenges to get here and what we had to overcome were definitely unique. And I'm really excited to hand it off to Delia to talk about the data infrastructure scaling work we've done, KV to talk about training and how we scaled up to that crazy 16K GPU number, and Charlotte for how we deployed at Inference efficiently and actually built real applications out of all of this.
Thank you, Joe. I'm Delia, and I will next share some of the cool insights about Llama-free data, as well as our investments towards data products to accelerate researchers' impact. As we build new versions of Llama, we invest in more tokens of higher quality and of better diversity. Notably, Llama 3 is trained on 7 times more tokens compared to Llama 2. It is multilingual, and adding languages beyond English required us to optimize the tokenizer for the best performance at inference time for non-English languages. This meant we had to increase from 100K vocabulary size to 128K. Data quality has been a major investment towards the model performance. And in the case of web documents, we have added 2 new quality methods. The first one, which we call Wikipedia score, measures the probability of any single document being referenced by Wikipedia. And second, we have used the previous versions of Llama to assess the quality of every single document that was candidate for training. Llama 3 brings significant lift in code, math, and in general problem solving and reasoning. And this has been enabled by better sourcing, extracting, and processing of such data, as well as very cool investments in synthetic data. I will give a few examples of the synthetic data investments. In the case of code, we add comments automatically, we add unit tests automatically. And we are using a process called rejection sampling, where the model generates tens of examples, and we use code execution signal as a feedback loop to decide what to keep and what to discard. We are also using synthetic data to annotate very long documents or long context, where it would be infeasible for humans to read such long documents at large scale. Data diversity comes in many forms: diversity of languages, diversity of modalities, and diversity of topics. In the case of languages, Llama is open source. Facebook, WhatsApp, Instagram are deployed across the world. Over time, we want to make Llama understand all the languages of the world so that it can speak to everyone and bring state-of-the-art AI to everyone in the world. Text comes in many forms. Web documents can be short, 2 pages long, or we have seen cases of extremely long web documents of tens of millions of characters. Then there is fast-changing short messages in form of dialogue, and we have code in all sorts of programming languages and all sorts of formats, from a simple function to an interview question, to a coding contest problem with unit tests, to an entire repository. And there is a lot of synthetic data advancements we have done in the case of code, and a lot of tricks in terms of how you flatten a repository into your context window. And then there is documents with heavy formulas like math and physics documents. And we have also noticed that interleaving code and math with text in the so-called editorials has helped the model. Llama 3 is trained on a wide diversity of topics, from historical facts about the world to sports, business, science, anything you name it. This enables the model to build a very detailed description representation of the world, and it enables it to answer questions across a broad diversity of topics and across different degrees of difficulty. We use all this data for training multiple stages of Llama, from pre-training to alignment to several stages of fine-tuning. And we also use it at inference time when users interact with Meta AI across our various product services. In particular, we index documents that are post-training time into our search engine, and we retrieve the relevant ones when the users interact with our products. Next, I will talk a little bit about the data lifecycle. For each type of modality, we need to decide where to source the data from, but it's equally important to also decide where to not source data from. In the case of web documents, for example, we don't want to get content that has too much concentration of personal identifiable information or adult content. With this data collected, we run several mitigations to make sure our privacy and integrity bars are met. For example, we want to remove documents that have harmful speech. And then to deeply understand every single document, we run a series of signals, such as language identification or various topic classification models. And we have a very extensive data curation pipeline, which I'll talk about in a bit. The purpose of the data curation is to filter out lower quality content. We have run extensive number of ablations or experiments before training in order to decide the best data mix we use for training. The data mix means the composition of different types of data, sports, art, math, code, as well as the degree of repetition. How many epochs should you run across your math content? We run this data mix on a model of smaller scale but the same structure as Llama. And we evaluated on the same set of benchmarks, reasoning, language understanding, multilingual, that we evaluate Llama on. And this enables us over time to correct gaps in our data and to come up with the best data mix for pre-training. We noticed, for example, that the internet has a lot of arts and entertainment, and we don't need that large amount to train Llama, so we downsample this content. We also noticed that upsampling science in general, math code, has helped the model performance. And we have done this throughout training and in post-training, including in a process called annealing, where we added more code, more math, and you can read more about it in our recently released paper. We create feedback loops from both data curation and from data ablations back into data collection. And these feedback loops enable us to decide what to collect next, focusing on higher quality and focusing on closing diversity and data gaps. Data curation for web documents starts with filtering out bad documents. We do this even at the URL level, and then extracting the content. We run a set of heuristics or statistics on top of these documents. You might have heard of the DeepMind's Gopher heuristics. You might have read the paper. So those are some of the kind of heuristics we are running. And then we run a set of deduplication algorithms to eliminate documents that are exactly the same, documents that are approximately the same. We use min hash algorithms for this. And also, we want to deduplicate lines that are very common, especially across the internet. And we are not in a one-size-fits-all situation. You want to eliminate lines heavily repeated in web documents. Those could be boilerplate. But you don't want to repeat lines that are heavily occurring in Python, for example. And then we run a set of language heuristics, language identification, and a set of models to assess the quality of the documents and the various topics in each document. We run all this pipeline in PySpark, and we use a lot of open source ML libraries that this community has helped build. Some examples are Presidio, various tokenizers, Beautiful Soup. Whenever we have to redo our HTML extraction or improve our quality algorithms or improve our deduplication models, we have to redo this entire pipeline across a very large corpus of data of hundreds of billions of documents. This is very expensive. And we have also observed data skew, where some documents are short, some are very large. So we had to dynamically shard the data into multiple buckets and parallelize execution in order to improve the efficiency and the latency of this pipeline. And with these changes, we are able to process tens of billions of documents within a day and create those feedback loops very frequently back into data collection. Our researchers are spending many hours to understand the data, compare data sets, compare training samples. And we invested in data products and tools to enable them to understand data faster, to make decisions faster, and to innovate faster. These tools include easy navigations of short and long documents of any kind, math, code, web documents. They include tools to compare data. And they include more advanced capabilities, such as integrating with Llama, where you can ask Llama anything about a document, and this has been particularly useful for very long documents where you don't have time to read through the document. We also added click of a button translation, which helps with multilingual, and we added collaborative capabilities such as annotating documents, adding comments, sharing documents with your colleagues, which have been very valuable for fine-tuning and eval data sets where data quality is even more important than it is in pre-training. We also generate data insights out of the box for all our training data sets. We create distributions of the data across all the signals and all the heuristics we compute. We also detect outliers. And one cool example is detecting repetitive text in Llama answers, such as the model repeating, I'm sorry, I'm sorry, I'm sorry. With these tools, our researchers were able to quickly detect such problems and correct them. So this gives the researchers a flexible platform for them to just move faster with data and improve the data quality. We have a lot more work in progress around multimodality, synthetic data, agentic behaviors, which we'll talk about over the next few months. Thank you. And I'll pass it to Kaushik to tell us some of the cool insights about training.
Thanks, Delia, for that fantastic talk on data. My name is Kaushik Veeraraghavan. In the next few minutes, I'm going to talk to you about how infrastructure has enabled the training of our large-scale LLM models, culminating in Llama 3.1 that you've heard about earlier from Joe. But before we jump into Llama, let me start off with a little bit of history. Meta has been a deep proponent of AI, and we've been using it really intentionally for the past decade. Specifically, if any of you have ever opened up Facebook or Instagram and looked at your newsfeed or have ever clicked an ad, well, that's our AI models for ranking and recommendations at play. So we've been deeply invested in this space. What's changed in the past year, though, is the scale at which LLM training has shown up and how we've evolved. Specifically, while we've been using a bunch of AI training for ranking and recommendations, most of our jobs ran on small numbers of GPUs, maybe up to 128 of them. LLM training is completely different, and we need to rapidly scale to hit 1K, 2K, 4K, and eventually 16K GPUs for a single training job, as you've heard from my friend Joe Spisak. In the next several minutes, I'm going to talk to you about what this means and how we've scaled. But to just plant an idea in you, the scale at which you're operating at is similar to planting a seed and then growing an entire mature tree in a single year. This is just crazy growth. In order to enable this, there's really two parts of the problem. The first is the physical infrastructure. We need to make sure that we've invested deeply in building out a foundation, which starts with the physical infrastructure, the data centers, the networks, the hardware, and so on that power our AI ambitions. And next, we have to invest deeply in building out the software stack and build out the operations muscle in order to be able to run these large-scale AI jobs. In the rest of my talk, I'm going to go delve deeper into a few things that we've done at the physical infrastructure layer and several decisions we've been making at the software layer in order to enable this massive growth. Also, as Joe mentioned, we are deeply committed to open source. I'm going to share with you how this open source thesis pervades a bunch of our work across infrastructure, and I'm going to hit on several notes on how we really believe in open infrastructure throughout our stack. And then I'll close out by speaking not just about what we've done and reminiscing in our Llama journey, but also thinking about the future. What do we anticipate running into in the future, and how we look to the broader community? So let's start off by diving more into our open infrastructure. Specifically, as you might have seen again from Joe, or maybe you heard from Aparna or other speakers who are talking about our AI work, Infra is deeply committed to the idea of open source and open infra. Specifically at the physical infra layer, we've been champions of releasing all of our data center designs and our network design via our open compute and open network initiatives. At the software layer, we regularly release papers for things like our scheduling systems, such as MAST, for our storage systems, and many other things to the academic community. And finally, we are super excited to release the code for a bunch of our products, and then even entire models themselves, as you're seeing with the Llama 3.1 release. We also do things like write blog posts, which cover what are our cluster designs, how do we operate them, and then share a bunch of learnings about operating this massive infra to enable all our AI work. Now, let's dive deeper into what are some of the details of our infra. I'm going to start off by speaking about our physical infra. And in the interest of time, I'm going to give you a couple of examples and insights that explain to you why we're building certain things and the problems that we're trying to solve. So at the physical infra layer, the first thing that we realized was that we had a bunch of data center footprints, and we could use this to power our applications and to enable all our AI needs. However, we quickly realized that in order to get maximal performance out of these AI clusters, we needed to make some new decisions. Specifically, what we observed was that most of these AI clusters run on GPUs, and in order to get maximal performance, we needed to run these GPUs at their high thermal density point. Specifically, we found that for our H100 GPUs that were used for Llama, we needed to run them at 700 watts. When we take a bunch of these GPUs where individual GPUs consume 700 watts, pack many of them into a single machine, and then pack a few machines into a rack, we find that the rack exudes a whole bunch of heat, which requires that we think of our data center space in a different way to handle cooling, the new rack placement, etc. Right? So this spurs innovation at the DC layer. Next, we realized that in addition to the DC itself, we needed to ramp up on completely new network technologies in order to be able to interconnect these GPUs and then present an entire cluster abstraction to the software systems and all the ML engineers. In order to do this, we had to very quickly ramp up on RDMA and other technology. So specifically, what we realized at this point is that there are multiple solutions that are out there. There's Rocky, there's InfiniBand, and there's these other ideas. Now, the challenge here is we didn't quite know which solution worked best. We could obviously read about it, but we wouldn't know what is our experience like. So in order to solve this conundrum, we created two 24K clusters, one outfitted with Rocky, the second one with InfiniBand, so we could get hands-on experience and learn about the networking challenges, as well as how to make full use of this cluster. Again, as Joe mentioned, the Llama 3.1, all the Llama models, especially 3 and 3.1, were trained on our 16K Rocky cluster. Now, beyond the physical infra, at the software layer, we realized that we had to start innovating in a few different ways as well. Specifically, we needed to build specialized scheduling system in order to be able to schedule 16,000 GPUs to be able to run a single job. We also needed to figure out how to build out the operations muscle to get the maximal effective use out of this cluster. So let's dive into this next. So a key tenet of these Llama 3 training jobs is that they run on thousands upon thousands of GPUs. And unlike our previous ranking and recommendation AI jobs, we find that these jobs run for weeks on end, right? So we had to figure out how to build a custom scheduler. And then we had to figure out that in order to exercise this cluster well and get maximal performance out of it, we needed to leverage every resource element that we had. Specifically, we had to start off by pushing the capabilities of each GPU to their max within a single machine. We had to figure out how to get the most out of the multiple machines in a given rack. We had to figure out how to interconnect these machines into a small cluster of about 3,000 GPUs or so. And then we had to figure out how to interconnect these small AI clusters into a single large training cluster that we could use for a job the size of the Llama training run. We had to build all this complex machinery, and it's all shared in our mass scheduling system. And by the way, you can go read about mass online. Now, it wasn't just enough to build out this physical infrastructure, get all the GPUs in place, and then interconnect them. Next, we needed to also figure out, yes, we can schedule jobs on them, but how do we maximally get the performance of this cluster to be high? In order to do this, we had to figure out how to map different modes of algorithmic parallelism onto the hardware that we had. We accomplished this by taking tensor parallelism across GPUs in a single server. We then ran pipeline parallelism across racks in a small cluster. And then we leveraged data parallelism to make full use of the entire training cluster, right? So we had to put all these different pieces together in order to be able to push our cluster to its limit. Next, we also had to figure out how to keep the training job stable. This is easy to say, but really, really hard to do. Because what we have is we have 16,000 of these GPUs that have to be in tight interconnectivity, operating at a nanosecond pace, and really working together in a synchronized and coordinated manner for weeks upon weeks on end, right? And what we found was the training job would unfortunately come to a stop anytime there was a single failing GPU, anytime there was network congestion or communication issues across these GPUs, or there were any bugs in the software stack. This was really challenging and daunting when we started off. But what we quickly realized was that we had tons of experience from running production online systems. We could solve this problem by investing and extending our investments rather in observability and debugging and identifying ways where we could quickly identify failures at the hardware network of the DC layer and then triaging these down. So we went about this work in two different ways. First, we leveraged a bunch of our software systems. For instance, we leveraged the flight recorder capabilities within PyTorch to capture every single communication event and its duration across the GPUs. Now, most of these would be held in memory. We would only dump them out anytime there was like a crash in the nickel watchdog timer or a heartbeat issue or something else, right? So we started getting telemetry and so on. Next, we invested in custom tools that allowed us to visualize performance issues. For instance, I developed a tool that allowed us to quickly debug slow collective communications and identify if the problem was at the communications layer or something going on in the compute kernels or in the hardware itself. And then these tools allowed us to quickly trash problems and then recover. The key takeaway or the key benefit of our observability and debugging investments was that we were able to achieve a 90% effective training time for our Llama 3 job. This was one of the most interesting things that I feel we learned through the Llama experience, and we're super proud to share this table with the broader community. So if you go to the Llama 3 paper, you can see it in gory detail. What you'll find is after running our job for a 54-day period, we ran into about 419 issues, of which the vast majority of them, about 78% of them, were due to hardware issues. I'm super proud of this work because it wasn't just the case that we were able to figure out how to quickly ramp up and in 18 months, go from running jobs on really small numbers of GPUs to these thousands upon thousands of GPUs. But further, we were able to figure out how to debug problems and get insights that allows not just us to plan for the future, but also the broader community to understand the science and the challenges behind operating these large-scale clusters. Now, as we look to the future, we feel like we're going to go way beyond what we're currently operating at, right? We expect to build even larger data centers and even more physical infrastructure. In order to keep pace with the growth that we anticipate in the future, we're making several changes to our software stack. For instance, we're overhauling our checkpointing mechanism by realizing that at a larger scale, we need to be checkpointing possibly even more frequently. And hence, we need to invest in things like in-memory checkpoints, writing snapshots to flash, as well as writing out snapshots and checkpoints asynchronously to persistent storage. Similarly, failure at the scale is inevitable, so we have to recognize that it's not enough to just save state, but also to invest in recovering from them. So we're optimizing how quickly we can load checkpoints back into memory. How do we do things like initialize large jobs and invest in nickel initialization speedups, as well as figuring out how to work on container restarts for the containers that run these AI jobs themselves. But it's not just software that we need to invest in. We also need to invest in the physical infra. For instance, as all of you are probably aware, GPUs are in scarce supply today, and we anticipate that they might continue to be in scarce supply. Further, we expect that the scale that we need to operate at is going to continue to increase. So how do we make use of the larger power or the larger clusters that we have? Well, we might need to outfit it with different generations of hardware. So for instance, it might not just suffice to use H100 GPUs. We might have to invest in the next generation of NVIDIA GPUs, and if need be, even in the previous generation, like A100s. So we need to now make sure that we can operate training on heterogeneous hardware from the same vendor like NVIDIA. But in addition to this, we might also need to run hardware of many different types. So we might need to operate NVIDIA hardware, but we might also need to run our own custom hardware, which is called MTIA. And then we might need to run training in a heterogeneous manner across all these different hardware types. Later today, you'll hear from Joel Coburn and several others about MTIA, so look forward to those talks too. Finally, at a very innate physical space, what we find is that it is really, really hard to get power and to build a single humongous data center. We just expect to run the laws of physics in acquiring power or maybe in connecting all the GPUs that we need to in a single homogeneous way. This brings up a new challenge. Unfortunately, the current training paradigm of expecting all the GPUs to be connected uniformly and then leveraging synchronous training might not work. So we might need to start investing in completely new research strategies, such as asynchronous training, which is only a research idea or research concept. We might need to figure out how to port that into a production environment. So we're starting work of that type as well. Overall, as you can tell, we feel like we're barely getting started. Over the past 18 months, we've accomplished a lot in figuring out how infrastructure can enable us to develop these Llama models and scale our training. Next, we'll hear from Charlotte about what we are doing in the exciting world of inference. We're super excited to collaborate with you on training, inference, and everything beyond.
All right, thanks, KV, for the great talk on training infra that generate the model for us to play with. I'm Charlotte, working on LM inference infra at Meta. In the next 10 minutes, I'm going to show you how we deploy Llama to real production. Meta launched LM-based applications since last Connect. We're doing everything for free. Many of you might know that LM inference is notoriously expensive to serve. The model is huge. The generation is iterative. Behind the scene, of every element response, like here. We probably run model.forward more than 50 times. That is because the generation for each token is conditioned on all previously generated tokens. Apart from product, we also have a lot of internal traffic that the user don't see, like synthetic data generation, knowledge distillation, rejection sampling. This offline inference workload is massive. To give you an idea, for Llama 3 ROHF, we have to process hundreds of millions of examples for rejection sampling, and we have to do that in a very short period of time, and for a few rounds. Fitting both traffic at scale and efficiently is very challenging. Let me walk you through our journey to make that happen. In a nutshell, this is the bin packing problem. You're feeding models onto hardware. We have a lot of models. That is because one LM application is backed by multiple LM inference calls. You got the main model for chat and a bunch of ancillary models for integrity, enrichment, reward, and everything else. We also get a lot of hardware from different vendors of different shapes. They are best at different type of workload because they supply different amount of GPU flops, HBM capacity, and bandwidth. To make an economic decision here, we really have to understand the system implications of the LM weights, preview decode operations, and KV caching. This is our problem statement. To start solving this problem, let's start by looking at our hardware boxes. Here, we got two hosts installed with H100. They got CPU to GPU, inter-GPU, and inter-host communication, all at different speed and bandwidth. It's almost like a mini distributed system that you are running into potential bottlenecks almost everywhere. Each GPU has 80 gig of HBM. I want you to really remember that number, and let's start fitting some models. Llama 3 8B fitting one GPU just fine. Moving to 70B. That is too big for one GPU. We have to use tensor parallelism to partition the model weights across multiple GPUs on the same host. Moving to our 405B model. Wow, the model weights in BF16 is over 800 gig. This is bigger than 8 H100 cards, and we have to keep some space for KV caching. This means you have to figure out how to do FBA quantization, or you find AMD MI300, which offers bigger HBM. Or you go with interhost pipeline parallelism to further partition the weights. Over time, we realized that preview and decode demand very different system resources. Preview is more compute heavy, and decode is more memory bandwidth heavy. We can disaggregate them into different services. This also helps us to mitigate the long tail decoding latency because of the interruption from long previews, which help us to maintain the same latency SLOs with much fewer machines. Long context models are getting more popular this year, which really create a big problem for us. That is because the GPU demand actually scales quadratically with context window, especially for very long context models. To give you an idea, running preview on 70 model with 1 million token is gonna take a few minutes. It's basically impossible to utilize that in very real-time application. If you don't want to use any approximation, you can use context parallelism to partition at the context dimension to allow you to further replicate the preview nodes and throw more compute and make things faster. If you want to run a long context model on 405B in BF16, you will need a little bit more mix and match. Here, we're mixing 3 types of parallelism. You got an 8-way tensor parallelism, 2-way pipeline parallelism, 2-way context parallelism, and a 3-to-1 preview decode ratio. Pretty complicated, right? And we have more interesting design over there. And when we're coming up with this system, we have to keep in mind to really make them compatible with all of the model architecture we are supporting, including some multimodal ones, speculative decoding, all of our custom kernels and customer inference engine. All right, so far, we've only talked about how to build a system that can serve a handful of LM requests. Next step is to take that system to real production. What you will see in real production? Well, you get more moving pieces. Your input length changes. You got peaks, troughs, and spikes just like all online services. Comparing to a fixed benchmarking environment, your batch sizes are smaller and varies. Your sequence length also changes. The input to output ratios are also different. And you also have to update your models frequently. We realize the closer your workload gets to production, the more you lose from these theoretical flops. And this gap can be easily over 10x. What does that mean for us? Well, it's a lot of hard work on performance. We're building the system to automatically select the best serving options for different workload. A lot of time, we're also asking ourselves, can we step back from the inference box? That is when you start seeing the non-inference latency and you see the fleet-wide inefficiency, which is sometimes make a lot of those absolute 10% performance gains not really that appealing to us. One of the biggest opportunities that you wouldn't be able to do a great job by only heads-on working on inference box is the prefix caching. For chatbot application, we put chat history and prompts all in the request. The KV tensor from previous turns are already computed. That is obviously some room for caching, right? We are doing this since Lost Connect. We keep a cache of KV cache on the host RAM, and we sticky route the request from the same session to the same host with consistent hashing. We also want to continuously improving the cache hit rate, and that means you want prompts that are more cacheable, and you want cache that is bigger. To make prompts more cacheable, we're working very closely with our product infra team to improve the prefix similarity for our prompts by co-designing how the multi-turn chat history management should look like. To make the cache size bigger, we are offloading the cache from RAM to flash to distributed caching system. Finally, let's try to hook up everything together. Put everything we built to real data center in front of real users in real time. Now let me bring back some of my fancy boxes previously. Imagine you're going to do allocation for all of that. It's gonna be pretty challenging, right? It's even more challenging because maintenance and hardware failures happen all the time, like KV also mentioned. Inter-host distributed inference require hosts that are physically closer to each other, which tends to fail together at the same time, and we don't like that for online inference service. Some of our workloads are preemptible, some are not. And you want to place your host in a few more regions, otherwise your network latency is gonna be longer than your inference latency. We are pushing a lot of infra boundary to solve all of these problems. We are building network topology-aware scheduling for online services, which is actually different from the one we built for training. We built deployment solver to deal with allocation and routing constraints. We keep evolving our auto-scaling, load balancing, and management for elastic instances with awareness of specific LM performance patterns. And lastly, we also have to abstract away all of these operating complexity from our product team. To wrap up, optimizing LM performance is all about optimizing compute time and data movement time. Building an LM inference engine is like building a distributed operating system. You are taking a very system-oriented approach looking at these model architectures, and we are solving problems like scheduling, memory management, optimizing communications, and accessing external resources. The product trade-off is also gonna be more complicated. Out of the 5 axes here, model quality, latency, throughput, cost, and reliability, you only get to pick 2 or 3 out of 5. There's no free lunch. We are continuously improving the maximum capability for all of our axes to get ourselves ready for the upcoming challenges, where we are expected to continuously drive down costs for more modalities, longer contexts, more agentic use cases. We're so excited to see so many innovative ideas in the LM inference efficiency area across academia and industry. And we are looking forward to building this strong and economic foundation with every one of you to be ready to run AGI in the future. Thanks everyone for listening. Now I'm going to hand back to my colleague KV to share his closing thought.
Thanks, Charlotte, for that fantastic talk on inference and what it takes to serve a global audience on Meta infrastructure. As AI training continues to scale to larger clusters and even more interesting ways of training, such as multimodal training, we expect to run into new infrastructure and algorithmic challenges. Specifically, we're going to figure out how to do things like build even larger clusters, invent completely new ways of interconnecting the GPUs that power these clusters, maybe by coming up with completely new networking paradigms or network communication paradigms. And then we're going to need to figure out how to run our large-scale AI jobs, schedule them on all these machines, take faster checkpoints, and so on. But more importantly, we're going to need to figure out how to survive the even more complex failures that we expect to encounter at even larger scale. If we get all these things right, then we might have a stable training job, which is able to use the cluster well. And the end output of that is going to be a trained model. Today, as you heard from Charlotte, we do a bunch of interesting things in terms of getting the models together, figuring out how to, push them out to our inference serving systems and such. But in the future, with even larger models, we expect that we'll need even more weights and even more biases. And what we also expect is that we can't really cut off individual models, and we might have to develop completely new paradigms like real-time updates of weights and publishing things continually. Equally importantly, we're finding that we need to deal with larger scale. And again, we now run into the challenge that we might not have a single hardware family to serve all these models. We might need to deal with this complex heterogeneous hardware deployment that's needed to serve our end users. And finally, we need to understand how the products use these models and understand how factors like latency affect the user experience. Because remember, our end goal is to make sure that people who are using our models can go about their lives and have a better experience. So we need to figure out how to serve our users well. As you can tell, we're super excited about all of our work on AI and the different aspects of scale, hardware, clusters, network, and so on that this encompasses. This is pretty amazing. We're super excited to collaborate with all of you. And equally importantly, we feel that it is super critical and important that we do this in an open manner. We plan to keep publishing all of our work in the open. We plan to keep releasing our models. We hope to keep working with the PyTorch community, as well as the open compute, open network, and other communities across our infra stack. Thank you for joining us on this journey.